Hello and welcome to another digital design class. Last week we had our exams. We didn't have a class on Thursday and I'm sorry, on Tuesday, and on Thursday we finished chapter 2 and we finished Boolean algebra, that part. This week we start with chapter 3, which is digital logic design, gate level minimization. The topics that we want to cover this week would be an introduction to gate level minimization. This refers to the task of finding an optimal gate level implementation of a Boolean function. And the reason that we want to simplify a Boolean function, again, is to minimize the number of logic gates. Then we will go through the map method. We already learned about Boolean algebra and the algebraic expressions and how we can use the theories and the postulates to be able to minimize the gates using Boolean algebra. And this week we will start with a different method, which is called the K-map or Karnaugh map, or the map method, which is a simple, straightforward procedure. It's a pictorial form of the truth table, and it applies only if the number of variables are less than 7. I'll explain why later on. It's going to create a multi-dimensional problem, which is going to be very difficult. After 5 variables, we only go up to 5 variables in this course, but it's not feasible for if the number of variables are above 7. The K-map is a diagram made up of squares, and each square represents one minterm. And as you remember, minterm, we can create the sum of products, or what we call a product. A little review of the Boolean functions and what we learned in the previous chapter. We learned about the sum of minterms, or what we call the sum of products. Sometimes in some books we show it with SOP. Sum of products. Or the product of sums, or product of max terms, which we call POS, the product of sums. We reviewed how we can get the minimum number of terms and minimum number of literals by using Boolean functions and Boolean theories. And we learned that in the previous chapter that the simplified version or simplified expression may not be unique. We may have 2 or 3 answers from a Boolean function, and all of them are right, all of them are correct. But again, they would have the same number of gates, but they are not the same. So this is other thing that we learned. Now, today our focus, and for the next class and next week, is going to be only on solving Boolean functions and simplifying Boolean functions using the map method, or what we call a K-map. This is, I would say, an easy topic, and usually you would have 1 or 2 questions from the maps on your FE exam as well. Learning it at beginning, it's going to be a little confusing, but if I would solve multiple examples, and I'll guarantee you, after you solve a few examples, you're going to get you're going to become an expert in this. It's going to be pretty easy. It's again, I would say a low-hanging fruit for your FE exam. This is going to be one part that you can easily get it right in the FE exam. So we're going to start with the two variable maps. First of all, the number of blocks or squares in a K-map is equal to 2 in a power of n. N is the number of variables. So if we have two variables, then we would have 2 in a power of 2. We would have 4 squares. For example, here we have x and y. Therefore, we would have 1, 2, 3, 4 squares in the K-map. What if I have 3 variables? Then 2 in the power of 3, I would have 8 squares. If I have 4 variables, I would have 16. And if I have 5 variables, I would have 32. Okay. Now, if I have 2 variables, x and y, the combinations would look like this. I would have xy, x prime y, x, y prime, and x prime, y prime. And from the minterms, the sum of products, we learned that, I'm going to write it like this. We learned that x prime y prime is equal to m0, x prime y is m1, x y prime is m2, and xy is m3. So again, I would have 4 different combination for the minterms here. So again, m0 is x prime y prime, m1 is x prime y, m2 is x y prime, and m3 is xy. Now, in a 2 variable map, again, we have 4 squares, and we number the squares like this: m0, m1, m2, and m3. And if I want to replace it with its minterm, x0 is equal to m0 is equal to x prime y prime, m1 is equal to x prime y prime, x prime y, m2 is xy prime, and m3 is xy. There's also another way that we can show this. The horizontal or the rows gives us the x, and the vertical ones, the columns, gives us the y. So the first row, x is equal to 0. In other words, we have x prime. And the second row, I have x equal to 1 or x. And for the columns, for the first column, I have y prime or y equal to 0. And for the second column, I have y. So again, first column is y prime, second column is y. First row is x prime, second row is x. Now, if one of these squares is 1, we will find which minterm or sum of product does this correlate to, and that would be our answer. So for example, this one is 1, the rest is 0. So therefore, we have m3 is equal to 1. Therefore, the function f would be equal to xy, which is equal to m3. Now let me give you another example. Imagine this is also 0. What if this one is 1, this is 0, and this is 0? Now, f is equal to m1, which is going to be equal to x prime y. Is it clear? Yes? Okay. Let me give you another example. Imagine now if I'm going to do it this one with green. This is 0. This is 1. This is 0. This is 0. What is f equal to? M2. And what is M2? It's x, y prime. M2 is x, y prime. And the rest is 0. Okay. Now, let me do it with a different color. Let's say, I don't know, yellow, orange or yellow. So what if 2 of them are 1? So I have 2 1s. I have a 0 here. I have another 0 here. If I have 2 1s, now I can combine these two together. And if I combine these two, let's go back. I see I have an x. So f would be equal to m2 plus m3, which is m2 is x, y prime, m3 is x, y. I can factor out the x, so it's going to be x, y plus y prime, and y plus y prime is equal to what? 1. So x times 1 is x. And here you can see that what is common between these two, or in this, it's going to be x. So f is equal to x. And you would see when the dimensions go higher, like 3, 4 variables, it's going to make it super easy, because you're going to find the common variable between the squares. Now on the right one, you can see another one. Here we have y equal to, you have 1, 2, 3 1s. And what I can do is I can put them, I have to put them in a pair of 2s. So I can put these 2 in one pair. And the interesting thing is I can use this one again and put it in a pair with the upper one. So I can use it twice. I can use this one over here twice. Now for the lower one, what is common between them? For the lower row, f is equal to x. And for the second column, f is equal to y. So I can say x plus y. Is that clear? Yes?
If that top one was moved over to the left side, would that be x plus y prime?
That's a perfect question. Yes. Let me solve and give you a few examples. Yes. So your question is if these 3 are 1s, yes?
Yes.
Again, I can combine these 2 and I can combine these 2. If I combine these 2, I would have x because I have x, and y is, and if I combine these 2, I have y prime. So it's going to be x plus y prime. Let me give you another example. What if this is 1 and this is 1? This is 0, this is 0. What would the answer be? So this and this cannot be combined. When they are diagonal, you cannot combine them because they don't have any variables in common. This is in Y column, this is in X, and that one is in X prime, and this one is Y prime. So F would be equal to X, Y. This one is X, Y prime. And this one would be equal to, this is X prime, this is Y prime. It's going to be equal to X prime plus, I'm sorry, X prime Y. So it's going to be X, Y prime and X prime Y. There's another way that we can write this as well. I can write it like this. I want to find the simplified version of the sigma of M1, M3, M0. Or I don't need to even write 1, 3. I can write 0, 1, 3. I want to find the sigma of 0, 1, 3. So this means this is 0. It's 1, 1, 1. So M0, M1, and M3 are 1s. I can combine again these two and these two. This is going to be X prime. This is going to be Y. So the answer F would be X prime plus Y. What if I have the sigma of 0, 1, 2, and 3? So sigma of 0, 1, 2, and 3. I can combine all 4. And therefore, F would be equal to 1. Because everything is and it's 1, so F is equal to 1. What if all 4 are 0? Then F would be equal to what? 0. It's not going to be 1 at all. Become 1. So 2 variable is very simple. It's 3 variable that it gets a little tricky. Now, if we have a 3 variable K-map, then we would have 2 to the power of 3, 8 squares. And the way that we number these 8 squares, we do it in the gray code sequence. It's M0, M1, then we skip to M2, and then we come back to M3. So M0, M1, M3, M2, M4, M5, M7, and M6. So you can see that these 2 columns have switched. If you want to memorize it, it's going to be M0, 1, 3, 2, M4, 5, 7, 6. And the way that we show X, Y, and Z, the variables, the rows are the X variables and the columns are the Y, Z. The second row is X. The first row would be X prime. The 2 first rows are Y prime. The middle row, the middle columns is Z. The 2 last columns are Y. Therefore, these these 2 will be our Z prime. So this is Z prime and this is also Z prime. Now let's solve an example. So imagine that this is 1, this is 1, and the rest of it is 0. So M3 and M7 are 1. So M3 plus M7. So 1, 1. What is common between these two bits? What variable is common between them? Which square does it fall in which I could say territory? Is it in the y territory, y prime, x, z?
Y and Z.
Perfect. So it's going to be y because it's in the y and it's in the z. So they share the y and the z. And if I write the Boolean algebra as well, it's going to be the same. This is equal to x prime y z, number 3, m3, y z prime. Sorry, y z. Yes, y z. And m7 is equal to x y z. So we can write it like this. It's going to be y z plus, or like this, x prime plus x times x prime plus x. X prime plus x is equal to 1, and yz multiplied by 1 is going to be equal to yz. So we can easily simplify them and put them in pairs of 2s. We can put them in pairs of 2s, 4s, 8s. We cannot put them in pairs of 3s or 5. It must be in the power of 2. So 2 in the power of 1, 2. We can't put 6 in together. It must be 4 or 8. 1, 2, 4, 8. So 1, 2, 4, 8, 16, 32. We can just put them in this order. So if I had 6 of these, I could put 4 together, another 2 together. But it's better to put 4 and 4. And I'll explain why we do that. Another thing to remember is this, we drew it flat as a 2D, but in reality, this map is like a ring, okay? So you're going to have, these are connected to each other. Just going to draw it like this. And this part is actually connected to the other side. So M0 and M2 are actually adjacent. They are neighbors. And M4 and M6 are neighbors as well. So if I have one over here and one over here, I can combine them together. These two are actually neighbors. So this is actually like a ring. By the way, we can only put the neighbors together and if they are in one row, same row or same column. So I cannot put these two together. This is wrong. I cannot put these two together. They are not neighbors. So this is also wrong. Okay. So again, these two don't go together. Let me draw it with the red. And also if they are far apart, like these two also do not go together, that one and this. Now, let's do some examples. So here, M0 and M2, these two are 1s, and the rest is 0. So 0, 0, 0, 0, 0, and 0. So I can simply put these two together because, as I mentioned, they are neighbors. Now, what do they have in common? The way this is Z, this is Y, this is X. So what variables are in common? They both are in the X prime row, and they are both in the Z prime column. So I can write M0 plus M2 as x prime z prime. And for the proof, we can write this one as x prime y prime z prime plus x prime y z prime. Then we can factor out the y prime plus y. And finally, we have x prime z prime. Same thing, we can do it for M4 and M6. So again, this is M4, this is M6. We can put these two together, and M4 plus M6. Again, they have the same x row and z prime, which is their column. So it's going to x. So as mentioned, this is actually like a ring. It's not like a... And these two come together, okay? Now I'll give you some examples. I'll give you a few minutes to think on it, and then I would solve it, because I think best way to learn this is through solving some examples. So first example, we want to simplify the Boolean function f of x, y, z is sigma of 2, 3, 4, 5. So 2, 3, 4, and 5 are 1, and the rest is 0. 2, 3, 4, and 5. And the rest is 0. And we only, again, we don't care about the zeros in the min term. We only care about the ones. But when we want to solve the max terms, that's going to be a different story. Does anyone have the answer?
X prime y plus x y prime.
Perfect. So I can combine these two, and I can combine these two. This is y, this is z, and this is x. So first row, they have x prime in common, they have y in common. So for these two, it's going to be x prime y. And for these two, they have x in common and y prime in common. So it's going to be x, y prime. X prime y plus x, y prime. Example number 2, again, I'll give you a few minutes. This one, it's a sigma of 3, 4, 6, 7. Does anyone have the answer? Did you get?
Y six.
Yes. So we have 3, 7, 4, and 6. I can put these two in one combination and put these two in another. So for the red one, it's going to be, by the way, this is y, z, x. It's common between y and z. So for the red one, it's going to be y, z. And for the green one, it's going to be equal to x, z prime. Because x is common between them, and also z prime is common between. So the answer would be yz plus x z prime. Now let's solve it for 4 adjacent. If we have 4 adjacent, again, we can combine them together, such as if we have M1, M3, M5, and M7, I can put all 4 together. Again, this is y, this is z, this is x, this is x prime. Now, what is common between all of these 4? So it's divided between y and y prime and x prime, but the only thing is common between them, it's z. So this m1, m3, m5, and 7 is going to give us z. And this is actually the proof of it for it as well. You can see it's x prime z times y prime plus y plus xz times y prime plus y. And if we simplify it, we get to z. And if we have all 4 corners, so 0, m2, m4, and m6, we can combine these 4 together, and all they have in common is z prime. So the answer would be z prime. Now let's solve one for, simplify one for sigma of 0 to 456. And again, I'll give you a few minutes to think on it. Does anyone have the answer? No? Do you want me to solve it? Okay. So 0, 2, 4, 5, 6. What we want to do, we want to maximize the number of pairs that we have. So I'm going to combine these 4. And if I combine these 4, I'm going to get z prime. And this is z, y, x. So these 4 would be equal to z prime. Now, the next thing I want to do, I want to, let me show you something before I give you the answer. If I just pick this one and I don't combine it with anything, the answer would be z prime plus m prime, which is x, y prime, z. Okay. How many variables do I have in this? I have the 3 variables, x, y, and z, and actually x prime. And how many gates would I have? I have a z prime, so 1 not here. I would have 1, 2, a 3 input AND gate, so 3, and also a y prime, so 4. So 3, 4, 5 gates I would have here. But I have to minimize this. And the way to minimize it, so instead of having y as z prime plus x, y prime z, I can combine these two, and I'm going to show it with green. I can combine it with the adjacent one. And now what I have is I have z prime again, but this time plus m4 and m5. So m4 and m5, if I combine these two, I would have y prime because it's in y prime and x. So I would have x, y prime. Now what I did here, I got rid of an extra gate and an extra variable. So I've further reduced the complexity and I simplified it. So again, the final answer would be z prime plus x, y prime. Can I go to the next one? Is it clear? Okay. So for the next one, sometimes they show it with x, y, z, sometimes they show it with a, b, c. Here, I wanted to give you an example of what it looked like when we have a, b, c. We have an expression of a prime c plus a prime b plus a b prime c plus bc. And we want to show it in the sum of min terms. And we want to find the minimal sum of product expression. So again, A, and we have B and C. Again, this is M0, M1, M2, M3, M4, M5, M7, M6. So this time we are going from the actual expression to the K-map. Instead of going from K-map to the expression, it's the other way around. And sometimes you have the question, like this. Now, before I start solving this, I just want to put out a note. When you have 4 minterms, you have combination of 4 of these minterms, you're going to have one variable as your answer. So if I have 4, my answer would be z prime. If I have 2 of them combined, like these two, then this would have 2 variables in it. So here I would have y prime z. And when I have 1, then I would have all 3 variables. So this one, if I have M7, it's going to be x, y, z. So you can see that the more that I pair together, I would reduce the number of variables that I have. Okay, so 4, I would have 1 variable. 2, I would have 2 variables, and 1, I would have just all 3 variables. I would have all 3 variables. And if everything is 1, f would be equal to 1. So I would have no variables at all, no literals. So for this one, I want to find a prime c first. A prime is in this row, so I'm sure that it's in the first row, and c is these 2. And by the way, I have 2 literals, so I would have a pair of 2. So this is going to be my a prime c. Next one, I want to find a prime. Again, it's in this first row, but it's in the b column. So it's going to be a prime b. It's going to be these 2. So this is a prime b. Next, I have a b prime c. So a, it means it's in the second row. It's in the b column. I'm sorry, b prime column, which is this column over here. This is b prime. And it's in the c column. So it's going to be these 2. So these 2, I'm sorry, it's just this one, because it's a, not a prime. So this goes to the previous one. I did a small mistake. And a b prime c is this one over here. So this is a b prime c. Let me draw the last one with green. And then we have bc. So b is going to be these 2 and these 2. So we would have them connected. Now what we have is we have M1, M3, M2, M5, and M7. And what I can do is I can combine these 4 if I want to simplify it. And if I combine these 4, I have C. Now I can combine these 2. If I combine these 2, I would have A prime B. So the final answer would be C plus A prime B. And I can also solve this with Boolean algebra as well. And if I do that, I would, again, I can combine this with this with this. So C is common between them. And then I would have B plus A B prime plus A. Then I can combine these 2. It will cancel each other out. So this one is A prime. And if I combine these 2, I could cancel A out, and this would be C. And AB prime would be left. A prime B would be left. So as you can see, the final answer is going to be C plus A prime B. Now let me give you another example. Imagine if we want to simplify f is equal to xy plus xy prime plus x prime y prime. I want to find the simplified version of this. And let me copy the, so it's going to help you, the K-map, so it will help you as well. So again, I have this function xy plus x prime xy prime plus x prime y prime. want to see if I can simplify this. Did anyone solve this one? Yes. So xy, meaning it's in the x row and the y column. So it's going to be these two. This is xy. Then we have xy prime. So it's going to be x, but this time in the y prime column. So this is xy prime. And finally, we have x prime, y prime. So x prime is going to be these two and y prime. So these two are x prime, y prime. Now to simplify them, I can combine these four And I can combine these four. If I combine the black ones, the one in the black square, I would have, what do I have? Y prime. And the ones in the blue gives us what? X. So it's going to be x plus y prime, or y prime plus x. And if you solve it using Boolean algebra, it's going to be more difficult, but you're going to get the same answer. Do you have any questions? No? Okay. Thank you so much. This is for the theory part of today's class. We're going to go to the lab and do the rest of the lab, which is from lab manual number 2. Thank you, and I would see you on Thursday. And on Thursday, we will continue with the 4 and 5 variable K-maps. We're going to start with the 4 and 5 variable K-maps.